Lesson 8.6, Writing and Graphing Exponential Decay Functions. This looks familiar. We just did this. We did exponential growth functions. And growth functions basically did this. Get bigger and bigger and bigger. Don't know if I give examples in lesson form or in class form, but what are some examples of exponential growth? Well, money, if you put it in the bank, keeps growing faster and faster. You got your classic petri dish with the amoeba in it. The more amoeba there are, the more amoeba that grow. And human population, or any other population, is typically looked at as exponential growth. The more people there are, the more babies they have, the more babies they have, the more people they generate, so on and so on. So now we're actually going to look at the opposite of exponential growth, exponential decay. And we'll do the math first. So y equals a times b to the x. It's the same exact thing. Yes, again. But the b is a fraction. It's a positive fraction, so we actually do this. It's greater than 0, but less than 1. Like 1/2. So let's graph one using a t-chart. So -2, and we'll throw it out here. 1/2 to the -2 is the same as 2 squared, because we flip it. Down below, that's 4. 1/2 to the -1 is just 2. Anything to the 0 is 1. 1/2 to the first is just 1/2, which is 0.5. And 1/2 squared is 0.25. So, -2, 4, -1, 2, 0, 1, 1.5, to 0.25. So this is exponential decay. And its domain is all reals. You can put any x value in. You're not going to blow up the calculator. And its range is y is greater than 0. It never actually hits 0. It keeps getting closer and closer and closer. My line here should actually be more like this. It gets closer and closer to the x-axis. This is a little bit confusing. If you can actually make sense of this, it'll save you. This is why we put it at the end of the exponents unit, so that you understand negative exponents. What's the difference between y equals 1/2 x and y equals -2 to the negative x? So there's y equals 1/2 to the x, and here's y equals 2 to the negative x. Well, if we have a negative exponent, we know we just throw it on the bottom. The whole value on the bottom. So it's like saying 1/2 to the x, which is the same as 1/2 to the x. So these are the same. We just defined a decay exponential function as having a fractional b value. But the other way could be saying that it's a whole number to a negative exponent. Either way is fine. It is not critical to know this, but it's critical if you really want to understand how exponential functions work. We're just introducing them, so don't get too hung up on it. Now back to how to draw the function. A times b to the x. We found the b value by saying what's being multiplied here. Since it's going down, we could say it's being divided by 5. We want to multiply, so it's like times 1/5. So b equals 1/5. And then to find the A value, we go here. Whatever when x equals 0, whatever y value we get, that's the A value, so A equals 1. So we get y equals 1 times 1/5 to the x. Domain, as we know, is all reals. And range, y keeps getting smaller and smaller, but never 0. Y is greater than 0. We want to do a quick graph. -2, 1, 2, up to 25. We'll go by 5s, 5, 10, 15, 20, 25. -1 is 5. 0 is 1. And then these are going to be barely above the x-axis. Same looking graph. Exponential decay. Starts out great, and then it gets smaller and smaller very rapidly until the point that we can't even tell the difference. So to summarize, exponential growth, y equals a times b to the x. B is greater than 1. Exponential decay, y equals a times b to the x. 0 is less than b is less than 1. So b is a fractional number between 0 and 1. 1/10, 2/5, something like that. Now, I did not give any examples of exponential decay, but there's a lot of them. The most famous one in engineering is nuclear material. Nuclear material actually loses its potency. It since there's, say, a kilogram of nuclear material, it starts to decay. And after a little while, there's a half a kilogram. And since there's less nuclear material, there's actually going to be less decay. So it slows down. So that's where you get this shape like that, where it decays rapidly at the beginning and then less so. Same thing applies if you have a car. Car loses value. You buy it, and in the first year or two, it loses a ton of value. But after a while, it gets so old that if it's 6 years old or 7 years old, it matters, but it doesn't make a huge difference. So here's our formula. Same as last time, except there's a minus where there used to be a plus. T is your time. R is your rate. A is the amount. So just simply plug it in. $20,000 car, losing 5% value each year. How much is it worth after 4 years? 20,000. 1 minus 0.05 to the fourth. Put it into your calculator. You get 16,290. The car loses a fair amount of value. Most cars actually lose value a lot faster than that, but that's just an example. Good luck. Get cracking on some problems.